Okay, this is lecture 6 for Calculus 1, and we're just going to list out some basic limits here. This is going to be pretty intuitive, most of these here at the beginning, and I just want to cover them just to make sure that they're getting covered is all. Okay, so one is we want to do the limit of sine of x as x approaches a, and that's going to be sine of a. Pretty straightforward, okay? And it's similar for all of the trig functions, okay? If we do cosine, tangent, let me get caught up here in my writing. Okay, and then also cosecant, secant, and cotangent, they work the same way. The limit of cosecant of x as x approaches a equals cosecant a. Same for secant. And cotangent. Okay. And I should add that this is assuming that a is in fact in the domain of those functions. And I see a mistake on the tangent there. I wrote tangent of x and it should have been tangent of a. Okay, so that's assuming a is actually in the domain. Like for instance, this one here for tangent. That would not work if a was pi over 2 because there's no such thing as the tangent of pi over 2. Okay, so in that case, that wouldn't work. But if a is in the domain of those functions, then you can find the limit of that function as x approaches a by just plugging a in. Okay, and that's also true for exponential functions. It's not only true for trig functions, but also exponential functions. If you want to do the limit of let's say, so in the book it says a to the x, but I'm using a for something else here. So let's just say b to the power x, okay? As x approaches a, that would just be b to the power a. And we're just going to limit ourselves to b being positive. I'm using b there because that's called the base. The a is the exponent and the b is the base. Okay, this is also true for logarithms. You want to do the limit. I'm just going to write natural log, but it's true for any logarithm. Okay, the limit of the natural log of x as x approaches a would be natural log of a, assuming a is positive in this case because the domain of natural log is positive numbers. Okay, and it's also true for root functions, the nth root of x, where n is any positive whole number. The limit as x goes to a would be the nth root of a. So what we're seeing here is that for all of these functions, to find the limit as x approaches a, all you have to do is plug in a to the function. So now that I've said that for these 9 functions, I just want to remind you that that's not true for every function. That's why I'm writing these 9 down. because it is true for these 9. What's true? The fact that to find the limit as x approaches a, all you have to do is plug in a. These 9 functions are pretty special because that's true. That's not true for every function. I want you to remember that. Okay? Some functions, if you want to find the limit as x approaches a, sometimes you can't even plug in a. Okay? And I'm going to show you, now I'm going to write down how many are here. 1 second here. There's a section here in the book called Special Limits. So I'm going to write down 4 functions here and their limits that are not as straightforward. Okay? So let's scroll these easy ones off. Okay, suppose you wanted to find the limit of sine of x over x as x approaches, well, here, let me do this first. What if it was as x approaches, let's say pi over 2 for just for a second, let's say that. Okay, then based upon everything we've covered so far, you could say this. That would be sine of pi over 2 divided by pi over 2, which equals 1 over pi over 2, which is 2 over pi. We could definitely say that based upon everything we've learned so far. Okay, but what if I want to say the limit as x approaches 0? Well, then it's not so easy, is it? Because then you would have 0 over, you would have the sine of 0 over 0, which equals 0 over 0. And we would have a problem then, wouldn't we? So this one's not quite so simple. And we're not going to prove these right now. Some of them we could prove in Calc 2. You can prove these now too, some of them, but it takes more work than I think we should invest right now. So I'm going to list out these. There's going to be 4 of them. I'm going to list out these limits. This one right here, the limit of sine of x over x as x approaches 0, that limit is 1. Okay? It's not obvious why, although there is a proof in the book if you want to read it. It starts at the bottom of page 31 and then takes up most of page 32. Okay? All right, the next one, the limit of cosine of x minus 1 over x as x approaches 0. That one says 0. If I just tried to plug 0 in, then I would end up with 0 over 0 again. Okay? Just like the one right above it. But that one came out to equal 1. This one comes out to equal 0. Okay? Let's do the limit of 1 plus x. So there's nothing wrong with that, right? To the power 1 over x as x goes to 0. So we would have a problem there because of the 1 over x as x goes to 0, 1 over x approaches infinity. And so we would have a bit of a problem there. This one is not at all, I don't think any way you would figure out what this answer is, because it's very surprising. The answer is the number e, which is about 2.71. Okay, and one more. The limit of e to the x minus 1 over x as x approaches 0. That one equals simply the number 1. So you should write these down if you want my opinion. There's 13 limits here. If I were you, I would make a list of these and start keeping track of some limits. Okay, memorize which ones you can. That would be a great idea. You're especially in Calc 2. If you take Calculus 2, you're going to have a long list of not just limits. Here you're going to have things called derivatives and things called integrals. And you're going to have a long list of those that you should keep track of. Okay, so I would write this list down and look at it maybe once a day for the next few weeks. Okay, if you could memorize them, that would be awesome. All right, now I want to do a theorem with you called the Squeeze Theorem. And then this will finally finish off the section that we're on, so then we can start something new next time. Okay, so now this is found on page, let me find it here. It's at the top of page 31. Okay, and here's what it says. I might change the wording just slightly a little bit to make it a little easier to understand. Okay, it says, if f, g, and h are functions with g of x between f of x and h of x, and the limits of f of x and h of x if those limits are the same, let's just call that limit L, as x approaches a, okay, then the limit of g of x as x approaches a would have to also be L. This is easy to believe if you look at a picture. Let's just suppose that A is, let's just suppose A is right here. Okay, and let's do F in blue and H in green and G in red. Okay, and maybe G is a really difficult function or something like that. It's hard to deal with, but maybe F looks like this, and maybe H looks like this. Let me move that A over just a tiny bit. Okay, and maybe G is just wacky, but it's between those two. Okay, and notice that the limit of both F and H as x approaches A, that limit is the same for both of those, right? So even if G is really hard to work with, you know for a fact that the limit of G of x as x approaches A will also be L. Well, I know my picture is, if you look carefully there, I kind of messed up there. The red part went a little bit below the green part. It's not supposed to be. It's supposed to stay between. but let's not get too picky. Okay, so the point is that G is being corralled down to a specific limit as x approaches a. And that limit is the same as the limit of f and h. Okay? Now, if f and h don't have the same limit as x approaches a, then you can't use this theorem. All right? So you could use that theorem for something like this. You could find the limit of x times the sine of x as x approaches 0. Okay? And here's the reason why this limit can be very, very easy. Okay, it's because we know something about sine. Remember that sine of x is always between -1 and 1. It bounces back and forth, right? So that means that x times the sine of x is always between x times -1 and x times +1. So in other words, let's just, I guess because I have to be careful about positives or negatives, but I could say this. It's always between the absolute value of x and the negative absolute value of x. Okay? In fact, it looks like this. I can actually graph it for you. Here's the absolute value of x. Looks like that. Negative absolute value of x looks like this. And x times sine of x looks like this. So you see, I can find the limit right here really easily without even actually calculating that limit. All I have to say is this. Let me erase that gray stuff here. All I have to say is, since x times the sine of x is stuck between the negative absolute value of x and the absolute value of x, and the limit of those two as x approaches 0 are both 0, then the limit of x times the sine of x as x approaches 0 also has to be 0 by the Squeeze theorem. It can be a very, very useful theorem. Okay? All right, now, I know this wasn't a terribly long lecture, but this finally closes off the section we've been working on for actually a few days now. This is section 1.3, okay, and it's been stretched across a couple of lectures, 2 or 3 lectures, I don't remember which. But we finally finished it off. And the next section starts a new topic called one-sided limits. Okay, it's a totally new topic, so I don't want to get into it here and just barely start it. I want to start that on a fresh day, so I'm going to save that for Friday. So even though this was only a 20-minute lecture, that's okay, and I'm going to stop it here. Okay. There's homework on Canvas. I don't remember off the top of my head if that's due Wednesday or if it's due Friday. If it's due Friday, just keep working on it and get it done. Okay? And then after that, I'll put up a new one. All right. Have a good afternoon.